Okay, so let's move to the fourth atomic diffusion mechanism. We call the interstitial C mechanism. It's CY interstitial C mechanism. And first of all, this is the diffusion process as time increase. And you can focus, first of all, I hope you can check what happens through A to E as time increase. And probably you can targeting on the diffusing atom B. So what happens here and finally here. So probably you will say, as time increase, you visualize a diffusing atom B moves from here to here. Actually, it's moved here from here to here. And the second thing, probably you visualize there's always a host atom at interstitial site, or some should be interstitial site, or some other like substitutional side. But anyway, you visualize some atoms be inserted into this crystal structure, right? And at figure A is number 3, and here will be number 2, and figure C will be number B. So always there's a host atom located in the interstitial side. So here, I want to say that the driving force here to drive interstitial C mechanism actually is there's always a self-interstitial defect. For example, there's always a self-interstitial defect nearby the diffusing atoms. So this will drive the interstitial C mechanism. So what is a self-interstitial defect? Actually, it's a host self, always talking about not a small cell atom. It's a host atom located at interstitial site. We call a self-interstitial defect. So from A to E, actually, you can visualize diffusing atom B, and there's a self-interstitial defect at number 3 at number 3. Oh, and this atom push the atom 2. So now the atom 3 locate at lattice point, then the atom to be pushed at self-interstitial defect or as a self-interstitial defect. Then number 2 push diffusing atom B, then the number 2 back to lattice point or substitutional side, then the diffusing atom B moves to self-interstitial defect site. Then B push number 4. So now number 4 become a self-interstitial defect, and diffusing atom B back to the lattice point, or what you call a substitutional site. Then the number 4 push number 5. So the same. So you can visualize from figure A, B, C, D to E. The diffusing atoms always jump between substitutional site and interstitial site. Okay, follow 2 steps. And there's always a self-interstitial defect here. Okay, so the atoms here always like exchange the site with an atom at substitutional site. So the atom at interstitial site always exchange the site with the atom at substitutional site. So this diffusion mechanism we call them interstitial C mechanism. 所以在这里基本上interstitial C 多一个 CY，其实它第一件事情就是它附近扩散原子附近要有 self-interstitial defect。那这个 self-interstitial defect， 它在 interstitial defect 前面加了一个 self， 它指的就是这个原子不是小的溶质 solute atom，no no， 它是 host atom， 所以它叫 self-interstitial defect。host atom 在 interstitial defect 站在 interstitial defect 上，所以as long as 我的材料里面有 self-interstitial defect，它就很容易启动这个 interstitial seam mechanism。但 but you need to consider the distortion, right? To check how often or how easy this interstitial seam mechanism happens, the distortion. So I give you an example in FCC. Actually, FCC is shown like here. It's a close packed structure, right? So it's quite, if you want to have a self-interstitial defect inside FCC, which means that you need to insert a host atom is this big and into interstitial side, no matter is in which type of interstitial side. It's a little bit difficult, right? For sure, that will cause large lattice distortion. So here, I'm going to show you that in your textbook, actually, they introduce 6 different self-interstitial defect in FCC structures. So here, the first one, A, would be the host atom located at octahedral site. And B will be the host atom located at tetrahedral site. This is octahedron, the center of octahedron. And this will be the center of tetrahedron. This we call the octahedral site, tetrahedral site. And the C we call the crowned iron. Actually is in between 2 phase centers. In between 2 phase centers. And if you try to link these 2 phase centers, you will get the vectors. And these vectors, this atom at 100 and this atom at 010. So these vectors actually use this to minus this one. So it'll be 1, -10. So this is a direction of these vectors. So this we call because this is belongs to 110 family. So this defect we call, first of all, because in between 2 phase center, we call it crowned iron. And based on its directions, vector directions, we call it 110 crowned iron. So regarding to the family part, actually you learn that 100, use this symbol, we call a family of directions, included 100, -100, and 010 or 01, -10, and 001 or 00, -1. So based on you link them together and figure out the direction of the vector, you can name it. Okay, so this is we call a crowned iron. And the DEF, the characteristic for this one, and this one will be 2 host atoms share only 1 lattice point. So this type of we call a split what? Split dumbbell, split and split crown iron. So this 2 atoms share 1 lattice point. We call it a slip split. And if it belongs to here, just directly share the 1 lattice point. And if you link them together, then the direction you get here will be along x-axis. So this type of defect we call a split dumbbell. And based on is the vector the direction, so we call it a 100 split dumbbell. And this is also 2 atoms share 1 lattice point. But this we call a split because actually it's not as close as this 2. It's a little bit separate. And if you link them together, and you also can get the direction for these vectors will be 111. So we call a 111 split for figure E. And this one is not that close. This it have it's a diagonal. So that's what we call a split crowned iron. Also, 2 atoms share 1 lattice point, and this is it's in between 2 atoms. So let's sorry, and okay, so for this one is I just highlight the location for this atoms 1, 0, 1, and this it would be 0, 1, 0. Then the vector, the direction for the vector would be 1, -1, 1. So it would be the family one, a family of 1, 1, 1. And for this one is split crowned iron, and also based on its directions, vector directions, you know it belongs to 1, 1, 0 split down the crowned iron, because so this is we have like 6 different types of self-interstitial defect, and as long as you observe this, all of this or one of this, any of this happen or presented in your materials, then this self-interstitial defect probably will cause the interstitial C mechanism, diffusion mechanism. But be honest, based on the distortion degree, we figure out that this one have this split dumbbell has the lowest energy barrier, which means that it's much easier to form this type of self-interstitial defect compared to others, which also imply that this distortion rate will be smaller compared to others. Okay, so in the following slide, we will focus on this type of split dumbbell as our example to demonstrate that what's the diffusivity, host diffusivity through this type of split dumbbell. So I'm going to draw this again. I draw two FCC single cubic together, and they have a shared plane. And at the center, in original there should be a lattice pointer here, but now you have two atoms close by, and they share one this lattice point. This we call a split dumbbell. Then based on as you link them together, you figure out that the directions, the vector direction is proportion along x-axis. So this split dumbbell we call them as 1, 0, 0. So don't forget our purpose here would be I want to answer the host diffusivity, the diffusivity of the host atoms through this interstitial diffusion mechanism. So what's the D0 and what's the energy barrier? Okay, so in order to answer this one, you need to figure out how this like atoms jumps inside this crystal structure, right? So I try to enlarge both these figures. So it is, in the beginning, it's shown like this. And what's the next? So you can consider them as a group. So either because this one is this atom compared to this lattice points go upper, so more close to this four, right? So we need to determine the possible jumping directions. So we need to determine how many possible jumping directions for this pair, this group. So there are two ways to allow this split dumbbell moves. Is either one can, as long as either one jumps, then you will visualize like this. For example, like this atom, if this atom jumps to here, then the bottom one will be back to the lattice point. Then you will visualize the split dumbbell was here, then now it moves to here, and also the direction will become 0, 0, 1. So this is 1, 0, 0, 0. This will be 0, 0, 1. So this is how the split dumbbell moves or jumps through inside these crystal structures. So back to here, how many possible jumping directions? If I consider the upper, like light green one, the nearest lattice point, uh, nearest atoms would be how many I have? It will be 1, 2, 3, 4, right? And for the bottom one, also the closest, nearest lattice point side or substitutional side will be 1, 2, 3, 4. So 4 plus 4, I got 8 here. And the nearest, the distance, small r, will be here, half plus half. Half square plus half square, and you have a square root of it. So, but you can, so will be like a divided by square root of 2. But here as you know, it's like higher than lattice point, but you can use the distance between lattice point to here, just because it's the you can use this to have less approximation。所以在这里的话，基本上，你可以看到这种他们的扩散就是移动的原子移动的方式，事实上是只要其中一个离开，那这整个 speed dumbbell 的另外一个就会回到 lattice point 上，那你就会看到这个 speed dumbbell 移动了。那还有几个 jumping 的 direction，因为它现在是上下的，所以你可以预期它比原来 lattice point 上面这个更接近这上面4个，所以对上面这来讲有4个，下面这个来讲有4个，那他们只要是，所以总共有8个方向，因为是上4个上面，然后4个下面。那距离的话，你可以直接用 lattice point 之间的距离就好，因为不会有 big difference，所以你可以用这个做一个 simple 的 approximation。然后它可以去任何一个地方，so it can jump to anywhere. So belongs to non-correlated jumps. So f equals to 1. So back to here, I use a z equals to 12. I equals z to 12. Then the r is here. Oh, not 12. Sorry, z equals to 8, and the r is the 1 a divided by square root of 2, and f equals to 1. So I got the differentiability for this split dumbbell will be substitute each parameter. So I got the gamma a squared divided by 12. And I also try to write it down. So the gamma equals to 8 times this mu. So I times the a. So I got this results. But this is the differentiability for the split dumbbell. But I'm not interested in here, right? I want to know the host differentiability, not the split dumbbell. So the host differentiability will be depending on how much split dumbbell I have, right? And because this diffusion actually is drive or motivated by this split dumbbell, so will be the same idea what we learned in vacancy mediated one is through that one is through the vacancy, but here is through this split dumbbell. So will be the fraction for this self-interstitial defect and the differentiability for this self-interstitial and times f. So xi/dif actually is the due to this, why is here is due to this self-differentiability of the host atom is through interstitial mechanism. If you have more split dumbbell, then host differentiability will be higher. If the di increase, also host differentiability will be higher. Okay. So xi/dif. So xi is under the thermoelectric, thermodynamic conditions, equilibrium conditions, then the fraction for this split dumbbell will be exponential gives split dumbbell formation energy divided by kT. Then I just separate them into enthalpy and entropy term. And the di I just copy this term here. So di is here times f. So after arrange them, then I I organize the temperature dependent term here, and the rest of part will be temperature independent term. So I can figure out this will be d0, and the temperature dependent term will be the total energy will be included this split dumbbell formation energy and also their migration. Oh, sorry, split dumbbell formation enthalpy and also the split dumbbell migration enthalpy. Okay. So this is just a quick reminder how to understand or how to know your system belongs to interstitial mechanism. The characteristic for this diffusion mechanism, interstitial mechanism, would be all the atoms are the same kind of atoms, and there are self-interstitial defect. There are self-interstitial defect, which means that the host atom locate at interstitial site. And split dumbbell would be the two atoms share one site. We call the split what? Split dumbbell, split or split crown iron. And this only due to have a higher distortion. So usually distortion that will cause higher energy barrier, so only easily happen in high temperature. 所以在这里的话，就是这种 self-interstitial mechanism，它主要是发生在就是材料里面都只有 host atom，然后附近就在这材料里面有 host atom，它是在 interstitial site。那在这里的话，它是 split dumbbell 的 defect， 是一种 self-interstitial defect， 那也可以是 crown iron 或其他的。那在 split dumbbell 这里 ，split 什么？像 split dumbbell split 或刚刚提到的 split crown iron，sorry， 它基本上都是两个去 share 一个 lattice point。但这种其实大家都知道，这种 interstitial 的这一种就是self interstitial defect， 它的造成的变形量很大，所以lattice 的 distortion 很大，所以它需要克服的 energy barrier 会比较高，所以它比较容易发生在高温。但这个 host atom 是怎么移动的呢？其实看这张这个图就可以知道，我的 host diffusing atom 事实上是靠这个self interstitial defect 来移动的，所以它的 diffusivity 才是 xi-dif。那这跟那个前面教的 vacancy mechanism 是很像的。我来找一下 vacancy 的 mechanism， 这里其实也是我的 host atom， 我先算出 vacancy 的 diffusivity， 然后我的 host atom 事实上是因为附近有 vacancy， 所以是 xi， 这也是 xv-dvf， 就是附近如果 vacancy 比较多，那它的 diffusivity 会比较高，然后 dvf， 因为它就是也是因为附近有 vacancy， 所以它才能帮助这个 vacancy mediated 的 diffusion， 可以吗？好，所以so based on here, we know that if I'm interested in what's the E, for these materials. Also the same idea. I can measure the D star at 3 different temperature and plot the log D star versus 1 over T. Then the intercept can help me to get the D0, and also the slope can help me to get the E. That will be included the formation, split dumbbell formation enthalpy, and also split dumbbell migration enthalpy. Okay, so today we just ended here.